Round of applause for Audrey.
Yes, absolutely. Upright button. Oh, there you go. You got it.
Good afternoon, all. I'm Jonathan Hernandez. A little bit about my background. I come from the geothermal power sector and now into the heating sector. So I traded megawatts for therms, but I'm very happy I did. And so really what I wanted to talk to you about is the implementation of technology. So there's a lot of handover from the drilling sector, from the geoscience sector, and how it really incorporates with thermal energy networks as a whole. So what we'll do is, we're Fort Brightcore. We're based out of New York, but we essentially cover the mid-Atlantic all the way west out to about Ohio, Michigan, and about down south to about DC. However, we have partnerships, whether it's academic or intellectual leadership. We have an office in Sweden that's actually helping a lot with our modeling capabilities for the long-term loads. Typically, geothermal modeling had been done on an infinite horizon 2D, problem. We're getting to the point of doing finite element, similar to oil and gas modeling, where it's more 4D history matching and long-term planning. We basically try to leverage the intellectual capital, whether it's master drillers, PEs, MEPs, mechanical engineers, designers, geologists like myself, to design these in a way that they are truly baseload and that we are not overheating the ground or cooling it down, which could be just as detrimental. It's to truly make a baseload solution. So what we discussed earlier about COP, it's about lift. It's about providing the temperature from the bedrock compared to the ambient temperature. And that delta T is relatively relatively speaking, to, let's say, a nor'easter, currently last week up in the Northeast, would bring temperatures down to about 25. But that bedrock at the Manhattan Schist, for example, is about 55 Fahrenheit, pretty consistent. What you can do is you leverage that so that you're not trying to bring up 25F to 55 or to 75. You're bringing 55F up to 75, and that's how we're using water, which is a great, basically, exchanger fluid to pull heat or dissipate heat depending on what you need. Just like the back of your fridge is a heater and inside the fridge it's a cooler. No different. What we've seen though is that the energy in is usually electricity for the pumps, as Audrey explained, but the therms in terms of heat energy coming out can be anywhere between 4, 5 to 1. We've seen studies and cases in Colorado where it's near 8 or 9 in peak seasons, right? Colorado Mesa. Mm-hmm. So what that means for us in the utilities in general, everything's going to be decarbonized through electrification. Copper is expensive. Studies to build new, 512 kilovolt lines is extremely capex intensive. So the best way to do it is if we're all going to go electric, let's use less electricity. And that's what geothermal provides. So when we discuss COPs, it's really efficiency. And so an air source heat pump trying to pull heat out of a blizzard to heat your home is still more efficient than baseboard, electric resistive heating, which is essentially a toaster. That is still more efficient. But even though if you go one further step into ground source heat pump, then that's when you're hitting 4 or 5 over a full year. And that's really what's great. And we also actually have some examples that use hybridized systems where air source can be the star of the show, pre-charge the ground source becomes the star of the show in the peak seasons, and everyone's a winner when it comes to efficiency, especially those who have to pay the power bills. And this is all fuzzed out, but one of the ways how we do this is these ground source then can either go to a plate heat exchanger and then actually into the heat pump to do either centralized or a specific CHP system where the forced air duct system uses that temperature change. So what really this shows is that ground source heat pumps is plug and play into traditional off-the-shelf HVAC technology. You don't have to buy a specific geothermal heat pump, just the ground loop that plugs into your HVAC system. Similar with the water-to-water. So those were water-to-air. This is a water-to-water. We also do hydronic. And in some cases, and I'll talk about a project that we're doing in Washington, D.C., which is a pilot program, new building technology is just as important as the ground loop, what we call the envelope. If you have a leaky building, your efficiency is not going to be great. New technology where we're looking at whether it's passive house, which is extremely efficient to the point they become cooling dominant and you have excess heat, we're able to transfer that excess heat into the domestic hot water load. So all of a sudden now you've also increased your efficiency on heating the water as well as the space conditioning of the air. So really what we're saying is proven technology with proven infrastructure and new building technology has really been a key. What the big points here are that the design stages, whether it's a retrofit or a new build, the gentleman was here no longer here had that question, is getting in early to be able to design the system as holistically as possible, even though retrofits are still available, and then engineering for efficiency and thresholds. Thresholds are important. Previously, let's say 24 months ago, these did not pencil. The Inflation Reduction Act has provided incentives for geothermal ground loops to provide a 30% upfront reduction in CapEx, plus another 10% if you use domestically sourced equipment, and another 10% if you are in a disadvantaged community or what was called an energy community. Think coal mines areas, things like that, oil and gas areas. So you can get up to 30, 40, or 50% off of the system in the ground, as well as what some like to call Division 23, or mechanical engineering systems in the distribution that are connected to that ground loop. So when it comes to retrofits or new builds, it has now become, in some cases, the most cost-effective solution. This goes back to, and courtesy of heat, great image. What we're seeing here is basically to service the customer through the thermal loops that we've discussed and vertical boreholes. So I'm here to talk a little bit more about drilling and how do we get these boreholes. So before, ground source heat pumps used what we called open hole or open well. Basically, you're talking to an aquifer. If you notice, I keep saying borehole and not well. For permitting purposes, we are not injecting, we are not pumping. We are leaving it alone. It's an overgrown soil nail. If you're familiar with the civil engineering, if you grout, you maintain the consistency. Actually, this is thermally enhanced grout, which gives it enhanced thermal conductivity so that you can essentially move heat quicker. You don't have to rely on Darcy flow or permeability as much. What we do in Brightcore, for example, is we've got fleet diversity. You have crossover with water well drillers on your truck mounted, or even coring rigs like your typical Copco or Borat Longyear rigs. Then you can go into track mounted, and this is more production style rigs. The typical ground source heat pump depth for these boreholes is about 500 depending on the legislation. And I say that because Brightcore is based in New York. We are proudly the last company on record to apply for a mining permit to do geothermal. Right after the governor signed off, we had spudded a week prior, and then the law changed, and that was it. But you can go now to depths of about 850. You don't want to go too deep. There becomes a point where there's stretch in the HDPE and parasitic load on pumping. There's a sweet spot, right? And there's not just the typical HDPE. There are other solutions. So let's say a 500-foot hole would get you about 2.5 tons of load per borehole. There are some high performance. I mean, what I'm telling you about is the Toyota Camry. There's Ferraris out there that'll get you 10 to 15 tons per hole using advanced thermodynamic principles such as turbulent flow. And these are called Rygans, for example. And these Rygans are a little bit more expensive. They go down about 1,500 feet. But if space is the commodity you're after, they are a great solution. And so even within the boreholes, there's a whole slew of technology that can basically be custom fit to whatever project you need. And then here on the far right, we're very proud of this. This is more of a retrofit. We can actually go into sub-basements of buildings, go down 600 feet using, well, yeah, I come from triples and super singles and doubles where pipe racks were 30 feet long. These are 3 feet. And it's a mechanical arm, but it'll get you 600 feet into the ground. And we've actually done this in Central Park West. And what's nice is track mounted in the middle and track mounted on the right. Gets through a lot of nooks and crannies, but can also go angled. It does not have to be vertical. And what that means is that you can have a small footprint on surface and maximize the thermal load and residence time for the loop to have access to whether it's dropping off heat or picking up heat, depending on the ambient temperature. A good example of this is when you have a lot of infrastructure to get around, and you don't know where to go. Classically, this just would have been a line of 20-foot off-center vertical boreholes, limiting your tonnage. And therefore, it may not be worth it and it may not pencil. But if you have angle drilling, you can create a rugby field out of a bike path. These are 5 foot off-center. You stagger, and those circles at the bottom are really at depth. So this is plan view and side view. And really the idea here is to show that these thermal energy networks and borehole fields are not just out in the middle of a park or in a large plain. They can be in a street. They can be in places where you wouldn't expect them to be. And we're seeing this actually take hold in a lot of campuses, whether it's large Fortune 500s, medical centers, universities, as well as small towns. And so the idea here is that the drilling technology comes from the mining sector. It's off the shelf too. Those guys had to be pretty accurate. But you're looking for a quartz vein in the side of a mountain. You know, you only have so many shots before they call it off and run you off site. So this is the kind of technology that we use to help integrate the technology, such as thermal energy networks or even case-by-case projects. This is our big project for 2024 for a thermal energy network. This is in Washington, D.C., historic district. It's called Berry Farms. We received funding from the Public Services Commission out of D.C. for this pilot project. And this is a really great example because the new developments are going to be passive house, extremely efficient. So the excess heat is going to go to the domestic hot water. We're really excited about that, and when we have the data, we'll be happy to share it, given the right NDA and the right authorizations. So with that being said, it's about 200 apartment sites, 2 different bore fields, and again, load exchange and load balancing so that A, the ground doesn't overheat and people don't overheat. Bless you. Going back to the incentives, that 30, 40, 50% incentives that I was discussing, those are federal and stackable on top of state and local incentives. For example, PSEG down where I live in Long Island has $125 per million BTU up to about a couple $100,000 as an incentive. Con Ed, Eversource, NatGrid, everybody is interested in these programs because, again, they're getting 5x, 4x what they're putting into the system in terms of efficiency, right? So this is kind of what we're touting here. I may be preaching to the choir as we're all energy-driven folks, but at the same time, we feel like, as Will said, we're on the bleeding edge, if you will, of what is possible out there. This isn't brand new. It's brand new here. But if you go to Holland, Sweden, Finland, Norway, I mean, these are places that have been doing this since the 80s. So, we're happy to take any questions on the implementation and the technology portion. Thank you.
Who wants to know what HDPE is?
Oh, high-density polyethylene. You may see them on sumps, lighting some sumps when you're out there drilling and doing a catch basin. But it's extremely resistant, flexible, strong material that is used either in industrial tarps or pipes. But that stuff is rated for 50 to 75, maybe 100 years with proper operation and maintenance.
It's fair to assume if you put a loop at your house that your great-grandchildren will be able to use the heat in that loop with the same exact pipe and no real maintenance required. We have almost 40 years on our HDPE loop at our factory in Fort Wayne, Indiana. And it's delivering double what it was designed for after almost 40 years.
I will also say these loops, kind of set it and forget it, but the HVAC technology will constantly improve. So what we see now is the snapshot of 2024. 2034, that COP may be 7 and that may be the new standard, which utilities would love, we hope. Less drilling and more efficiency just overall because the transition is calling for electrification. And we can't all be jumping on the grid all at the same time during the peak time. I mean, it's no different than a bus or a train. If we're all trying to shove ourselves into the same cart, it's not going to work. So
make room for all the electric cars.
Exactly. No, it's true. And coming from the geothermal baseload power sector, I mean, that's another whole conversation.
What's the total size of the borehole?
Between diameter? 6-inch to 8-inch, depending on the depth. We telescope, similar to typical well designs. We case through the unconsolidated typically until we sock it into bedrock, and then afterwards, bedrock is easier actually to drill. But we'll go mud and then do air mist and or water hammer.
So very similar to well.
Exactly. We Tricone, PDC, we use the same toys.
Before Eric gets up to wrap up with the last presentation, those of you that are students, we would love to have, all of us would love to have you come work for us someday. We're always looking for more resumes. And the rest of you that are grown-ups, pardon the expression, we love to collect your business cards before you leave. And particularly North Texas Council of Governments, you need to know Audrey, for instance. But before you leave after Eric's done, let's make sure we make some connections and we can follow up with you in the future.
Can I, since it looks like we have time, can I just ask, are people confused by the concept of heat pump? Or you're all okay with it?
It's an unusual crowd.
Yeah, yes,
great.
that's awesome. Okay, I just want
We got time to go over the ideal gas law. It's not a problem.
if there are basic questions of any kind, just ask them, because there are I've asked so many dumb questions over the years that I love when anybody else asks me a question I can actually answer. So it's just a plus. Anyway, sorry.
Time for Eric Bosworth.
Thank you all.
Thank you.